Hello. Uh, Myself, I am Shesh Chaudhary, and I am the PMRF TA for this course. So, uh, along the course run, I will be taking 12 to 13 live discussion sessions where we will be solving some problems and also revising the theory, which is theory or the concepts which are actually being taught to you during the by the course instructor, right? I am Ashish Chaudhary. I am research scholar at IIT Kanpur, and this course is and C60 Geosynthetics and Reinforced Soil Structures by Professor K. Rajagopal. So, so before we begin, what we will be doing is that every week we will be revising all the concepts that have been taught in that week, and then we will be solving some of the problems. As today is the first, today is a discussion for the first week, so it has to be problem solving session. But in the first week lectures, if we have gone through them, we saw that there are no actually something like there are no problems. Okay, so basically it was just a discussion on some theories, normal literature on geosynthetics, their history, the types of geosynthetics, and some of their applications were discussed. So what we will be doing is that first of all we will be solving some basic problems from basic soil mechanics. Okay, just to brush up or just to revise those concepts of basic soil mechanics just for some time, and then what we'll be doing is that we will be mm, revising the theory that has been taught in this week. Okay, so we won't be solving any problems regarding the topic because there aren't any, right? So from the next week onwards, when we enter into designing and all, so from next week we'll be solving problems related to this geosynthetics topic. But for today, we will be just revising and discussing the uh, theory part from from the first week because there was only theory part in this week. And initially, we will be starting our today's session by solving some basic problems from basic soil mechanics. So some problems related to shear strength and some problems related to this earth pressure. Okay, one or two problems related to earth pressure and some problems related to shear strength. Just as to revise the prerequisite for this course, which is nothing but our basic soil mechanics, right? So let us start. Okay, so this is a brief introduction from my side. So myself, Rajesh Chaudhary, a PhD student at IIT Kanpur. So I am basically from Silchar, which is a city, which is the second largest city in Assam after Guwahati, and I completed my BTech from NIT Silchar in 2020 and joined the PhD program directly at IIT Kanpur thereafter. And I got selected as a Prime Minister's Research Fellow last year. And from after that, I am taking this live interactive sessions. In the previous semester, I took the session for this geology and soil mechanics course, and this semester I am taking for this course. Okay, I have given the link for my website, so you can get all the details in that, and also I've given the link for my LinkedIn page, so you can get all the details regarding me there. And if you have any queries, please feel free to write to me at my email address, which I have mentioned here. Okay, so this sessions will, I hope that we'll have an enjoyable time during these interactive sessions, and I hope that this will be like a two-way, like not just a one-way thing. So I hope that you will also give me some input, and together we will make this session a little bit interesting. We will try to make it. This we will try to make it a little bit interesting. Okay, so in the beginning, let us just start by solving some basic problems, right? Some very easy problems from basic soil mechanics, as because this first week lectures there aren't any problems. It was just theoretical part. On the next week, we will be starting solving problems from the geosynthetics part. After you learn about the designing and those things get taught. So let us just recap some of the problems from regarding basics, this shear strength and earth pressure theories. Thus, you will be solving some problems, and then what we will do, we will be revising whatever has been taught in this week. Okay. And yeah, I know these 2 hours actually is a very it's a very long time, but these are the actually guidelines by PMRF. So they had NPTEL had to make these sessions 2 hours long. So previously these sessions used to be 1 hour long, but now the sessions has to be made to 2 hour long sessions to satisfy the criteria. Okay, satisfy our teaching criteria. So that's why these are actually long. So you can take breaks in the middle, there isn't any problem. So you can join anytime in between, and moreover all these sessions will be actually uploaded in a YouTube playlist. So we will be getting the link of these videos. All these sessions are actually recorded, and all this will be actually uploaded, so you can also refer to them anytime later. So there isn't any issue. Okay. Let us start by solving some problems from basic soil mechanics. So the first problem is we have to compute the shearing strength of a soil along a horizontal plane at a depth of 5 meter in a deposit of sand having the following properties. Okay, so the angle of internal friction is given, dry unit weight is given, the G value is given, G is nothing but the specific gravity, right? G is given, and now it's also said that assume groundwater table at a depth of 2.4 meter from the ground. Okay, this is the first case. And then the second case is that we have to determine the change in shear strength if the water table rises up to the ground level. Okay, so let us start solving. So there is a this 5 meter, okay, right? So there is a sand layer, okay, which is 5 meter deep, and we have water here 2.4 meter. Okay, there is water. So you need to find the shearing strength of soil along this horizontal plane, okay, at a depth of 5 meter from the ground surface, right? So what we need to do, so what is the expression for my shear strength? Pick what is this shear strength equal to? If anyone can help me with that, if you remember, you can turn on your mic and just answer. Okay, what is the expression for shear strength? What is tau equal to? Tau is nothing but C plus sigma tan phi, right? So C is the equation. This sigma is nothing but the normal stress on that plane, and my phi is our internal angle of internal friction, right? So what is the C? As this is sand, so C is 0. So we need to find this sigma, and phi is given, right? So now see, this dry unit weight is given to us, right? So dry is given to us as 17.06 kilonewton per meter cube, correct? So from that, what we can do is that see, dry, right? So dry is equal to G gamma W by 1 plus C. So from here, what we can do, we can find out our void ratio, right? Nothing but G gamma W by 90 minus 1. So if you put all the values, G 2.65, W is 9.81, 06, so we're getting this as 0.546, right? Now what we can do, we can find out this submerged unit weight. nothing but G minus 1 plus C into gamma W. So G is 2.65 minus 1 plus 0.546 gamma W. So this will be, I think, 10.73. Okay. So now let us find out this effective stress, this normal stress, effective normal stress at this point. So it will be 2.4 into the dry unit weight of sand into 5 minus 2.4 into the submerged unit weight of sand, right? So this will be 2.4 into the dry unit weight plus 2.6 into the submerged unit weight. This will come out as 68.2. So finally shear strength comes out as 68.2 into 1038 into 53.76, right? Now the next part is the change in shear strength if the water table rises to the ground level. So if the water table rises to the ground level, what will change? This sigma is going to change. So this sigma will be nothing but 5 into 10.723 equal to 53.615 PA. So then our new shear strength is nothing but 53.615 into 10. Okay, so you can calculate this, right? Okay, so it was very easy, simple and straightforward problem, right? So okay, next problem, a standard specimen of a cohesionless sand was tested in a triaxial compression test and the sample failed at a deviator stress of 482 kPa. When the cell pressure was 100 kPa under drained conditions, find the effective angle of shearing resistance of sand. Okay, we need to find the 5N. Okay, the deviator stress is given and the cell pressure is given. Okay, at failure, what would be the deviator stress and major principal stress at failure for another identical specimen of sand if it is tested under a cell pressure of 200. Okay, these are two parts, right? So let us first solve the first part. So the deviator stress at failure, it is given as 482 kPa, right? And what is my cell pressure at failure? It is 100 kPa. It's nothing but my sigma 3. Okay, we need to find our phi, effective angle of shearing resistance. Now what is my major principal stress? Is nothing but deviator stress plus sigma 3. It's nothing but 482 plus 100, 582 kPa. Now we need to find out phi, right? So for that, what we will be doing is that we will be taking help of the our basic equation, right? The main equation for which is we derived from the this Moore column theory, right? So it is nothing but sigma 1 dash equal to sigma 3 dash 10 square 45 plus 5 by 2 plus 2ic tan 40 plus 5, right? So this we know, put here, right? This is 100 10 square 45 plus by 2, and C is actually 0 because it's sand, cohesionless sand, it's mentioned in the problem. That means C is 0. So if we solve this, we will get our phi dash as 44.1. Okay, now let us come to the next part. Okay, the second part. So what would be the deviator stress and the major principal stress at failure for another identical specimen of sand if it's tested under a cell pressure of 200 kPa? So same we will be taking help of the same equation, right? So sigma 1 dash is sigma 3 dash 10 square 45 plus 5 by 2. This is given 200. Same specimen, so phi is going to be same. 1164. Okay, so this is the major principal stress, effective major principal stress, right? Now if this is the major principal stress, what is my deviator stress? What is the deviator stress? Anyone can answer, there isn't an issue. What will be the deviator stress? Nothing but sigma 1 dash minus sigma 3 dash, right? So 1164 minus, what is sigma 3? 200, 2, right? Okay, okay. Uh, yeah, the third problem. So two identical soil specimens were tested in a triaxial apparatus. The first specimen failed at a Davidrix test of 770 kPa when the cell pressure was 200 kPa, right? So this Davidrix test is failure is given 770 kPa when the cell pressure means sigma 3 was 200. The second specimen failed at a Davidrix test of 1370 kPa, 1370 kPa when cell pressure was 400 kPa. We need to determine the value of C and phi analytically, right? So same, we will be using the same basic equation, and we will be getting two equations, and we can solve two unknowns for two equations to get our C and phi, right? So sigma 1 is equal to sigma 3 10 square 45 plus 5 by 2 is 2ic 10, right? So sigma 1 is 770 plus 200, 200 10 square 45 plus 5 by 2 I see 10. So this is one equation, and similarly we will be getting another equation. 770 is equal to 400 10 square 45 plus 5 by 2 plus 2 right? So if we solve these two equations into, we will get phi as 36.87 degrees and CS 52.5. Okay, now it's written, if the same soil is tested in a direct shear apparatus with a normal stress of 600 kPa, estimate the shear stress at failure, right? So we know C and phi, so failure will be nothing but C plus phi. C is 42.5 plus sigma is 600, it's given, and so it is nothing but 492.5 plus. Okay, very simple. We are just using the same basic equation to get our answers. That's all. Okay. So next, in a CD triaxial test was conducted on a normally consolidated clay, yielding the following data. The minor principal stress is given 250 kPa. Deviator stress is given 275 kPa. So we need to determine angle of internal friction, angle at which the failure plane meets with the major principal plane, and normal stress on the plane of maximum shear stress. Right. So if we remember the plane of maximum shear stress and the plane of uh, and the shear stress as the failure plane, right? Those two are different quantities, correct? The normal the ma maximum shear stress, right? The maximum shear stress and the plane of the maximum shear stress and the failure plane, at both this plane the shear stresses are different. At the failure plane the shear stress is not maximum, right? It's a different plane at which the shear stress is actually maximum. Here we are asked to find out the normal stress on the plane of maximum shear stress, right? And also the angle which the failure plane makes with the principal plane. Okay, that's fine. So let us try to solve this. So the test is a CD triaxial test. Okay, so CD triaxial test. For CD triaxial test, if you remember, for normally consolidated clays, the C value is 0. Okay, we will be needing this fact. So we should recall that for CD triaxial test, that for E of normally consolidated clays, the C is actually 0. Right? Now, this sigma 3 is given to us 250 kPa, and this deviator stress is given 75 kPa. The sigma 1 will be sigma 3 plus sigma t, but 525 kPa. Okay. Now, yeah. Now again we will be using the same equation. Sigma 1 is equal to sigma 3 10 square, or 35 plus 5 by 2 plus. Now, as I said, for CD test for on NC clays, normally consolidated clays, the C value is generally 0, right? So C is 0. So we can put all the values 5 to 5, 250. So 5 will be 20.76. 20.76. Okay. So we can get the 5 from here. Now next thing is angle which the failure plane makes with the major principal plane. So this is nothing but phi theta is equal to 45 degree plus 5 by 2. So 45 degree plus 20.78 by 2 is nothing but 55.3 degree. So the failure plane makes this much angle with the major principal plane. Okay. Okay. So say this is the sample, right? So this is sigma 1 having sigma 3. So this is the major principal plane, right? So this failure plane will be actually making this theta degrees. Now the third part, the normal stress on the plane of maximum shear stress, right? So for that it will be normal stress is equal to sigma 1 plus sigma 3 by 2 plus sigma 3 by 2 cos theta. So you know 5 to 5 plus 250 by 2 plus 5 to 5 minus 250 by 2 cos 2 35. We solve this, we get 338.72 kP. Okay, this is the normal stress at the failure plane. Okay, this is the normal stress at the failure plane. Okay, this is normal stress at failure plane. Now what we need to find out, normal stress on the plane of uh, this max. Let us find out the maximum shear stress. Okay, let us find out the maximum shear stress. Now shear stress first, the shear stress as failure plane. So shear stress at failure plane is theta. So if we put all the values, it will be 128 point. Now this is the shear stress at the failure plane. So if we recall the Mohr circle, say this is the Mohr circle and this is the failure envelope. Okay, this is the failure envelope. So this is the point of the failure plane, right? And the maximum shear stress is actually the diametrically opposite point, right? The center. This is the plane of the maximum shear stress. This is the maximum shear stress. This is tau max. And the shear stress here, it will be tau f. So this tau f, so the plane of failure is not the plane of maximum shear stress. So the shear stress at failure plane is 120. But what is the maximum shear stress? Nothing but sigma 1 minus sigma 3 by 2. It's nothing but 3.5 kP. So this 128.54 is the shear stress at the failure plane, but this shear stress is not the maximum shear stress, right? The maximum shear stress is this much, this much. So the sample actually does not fail always at the plane of maximum shear stress. It fails at some critical combination of a normal stress and the shear stress, right? And at that failure plane, the shear stress is not maximum. At that point, the shear stress and the normal stress actually make a critical combination, and that becomes the failure plane, right? So the plane of failure is not the plane of maximum shear stress, and failure does not occur at the plane of maximum shear stress. The failure occurs at a point where the shear stress and the normal stress have some critical combination. Okay. Okay, so the next problem, the results obtained from a series of CU tests on a soil gave the following results. So we have the values of C given to us. So CCU is equal to 0, C prime is equal to 0, and phi value is given 70 degrees, and the effective value of phi is 34 degrees. Okay, okay. Total stress value is 17 degrees, and the effective stress value is 34 degrees. If the sample of the soil was tested in a CU test under a cell pressure of 180 kPa, determine the deviator stress at failure, pore water pressure at failure, major principal effective stress at failure, and minor principal effective stress at failure. Okay. First, let us find out the deviator stress at failure. For that, what we can do? We can simply find the major principal stress. Major principal stress first. Right. Sigma 3 is given 180 squared 45 plus 17 by 2. Nothing but 328.74 kPa. Therefore, the deviator stress at failure, deviator stress will be sigma 1 minus sigma 3, 228.74 minus 180, thing but 148.74 kPa. Alright. Now the next part is we need to determine the pore water pressure at failure. So this equation that we wrote, this equation was in terms of the total stress parameters. That's why we use the 17 degrees. This is the total, not the effective angle of interpolation, right? Now to determine the pore water pressure at failure, what we'll be doing is that we'll be writing it in effective terms. So sigma 1 prime, sigma 3 prime, 10 squared, 45 plus prime by 2. This is nothing but sigma 1 minus the pore water pressure plus sigma 3 minus the pore water pressure, and 10 squared 45 plus 34 by 2. Now, sigma 1 value I know 328.74 minus u. Sigma 3 value I know 180 minus u. If we just solve this, we can get u is equal to 121.37 kp. Okay, very simple. Now the major principal effective stress at failure. So that's more simple, right? You already the major principal stress at failure means sigma 1 dash nothing but sigma 1 minus u is 328.74 minus 121.37 but 207.37. All right, and the last is the sigma 3 dash. Same, sigma 3 minus u 180 minus 121.37 50.63. Correct. So quite simple, right? Okay. Now let us solve one or two problems from this retaining wall topic, because this is important, because see, we use geosynthetics regularly in retaining walls, right? For reinforced to reinforce the for say to reinforce the soil, we to build reinforced soil structures, right? We use geosynthetic material, right? And also geosynthetic materials such as geotextiles and all, these are actually used as for a drainage, to help in the drainage of water, so that we will see that if water is there, the active thrust increases by leaps and bounds, right? It increases significantly. So our main task is not to allow water to remain. We should allow the water to easily pass, drain out from the soil, from the backfill soil of the retaining wall, right? So for that, what do we do is that we apply a filter material of some geosynthetic, so that the water can easily drain out, because this water pressure is actually very huge, and there are several cases where retaining walls have actually failed due to this problem of um, this thrust due to extra thrust due to active thrust due to water, right? Lateral thrust due to water. Okay, so first problem is actually very basic problem. So here a retaining wall of 10-meter high retains a cohesionless soil, with the angle of internal pressure 35 degree. The surface is level with the top of the wall. The unit weight of the top 3 meter of the fill is 1.6 ton per meter cube, and that of the rest is 2 ton per meter. Need to find the magnitude and point of application of the resultant thrust. Right. Okay. So just draw it. So we have this some 10-meter high retaining wall, right? Down we have this retaining wall. So the top 3 meter, this gamma is 1.6 ton per meter cube, and this bottom 7 meters 2 ton per meter cube. So what we need to do is that we need to find the magnitude and point of application of the resultant active thrust. Means we need to find the point where the resultant active thrust is actually going to act. Okay. So can you please tell me what is the expression for this active earth pressure coefficient? How can we find out this active earth pressure coefficient? What is Ka? Please, anyone can answer. Okay.
Yeah, passive pressure.
Yeah, no. What is the expression for K? K value. What is the expression for active earth pressure coefficient? How can we find out the active earth pressure coefficient? So this K is related to phi, right? Angle of internal friction. So what is
1
that?
minus sin pi by 1 plus sin
Yeah,
pi.
yeah, correct. 1 minus sine phi by
1 plus
1
sin
plus
pi.
sine phi. Okay. So 1 minus sine 35 sine 35. Okay. So if we do that, we will be getting 0.271, right? Okay. So now there are, see, this is the wall, right? So for first 3 meter, the pressure triangle will be something like that, right? So what is the value here? It's 3 meters. Small p1, it will be nothing but 0.271 into 16. Let us say g is equal to 10. Okay, 10 meter per second. 16 into 3, right? So this will be this length. Say we are plotting the pressures in this direction. So this is p1. Now for the bottom layer, the bottom 17, this bottom 7 meter. So this will be constant here now, right? So for the next bottom, it will be something, the pressure triangle will behave like this, something like that. Okay, and what will be this? Be nothing but 3 into 1.6 plus 7 into 2 into 0.27, right? And what is just this part? This part is nothing but 0.271 to 20 into 7. Okay, sorry, we just correct 16 and 20. Okay, now to find the magnitude of the resultant active thrust, what we'll do, we'll just take the areas of these triangles, right? We'll just take the area. So we have total PA is half into 3 into 13, right? So for this one, so what is this one? 0.271.
Recording in progress.
Yeah, just sorry for the this glitch. Just a second. Yeah. So what is 0.271 into 16 into 3? It is 13 kilometer per meter square. And 0.271 into 20 into 7 will give us 37.98. So first we are taking the area of this triangle. It's nothing but half into 13 into 3. right? So half into 3 into 13 plus area of this rectangle is 7 into this 7 into 13 plus area of this triangle, which is half into 37.98 into 7, half into 37.98 into 7. All right, so if we add all these, we get 243.3. okay. So this is our resultant total active thrust that is acting, right? Now we need to find out the point of application of this active. So where is it actually acting? This PA, where is it acting? So for that, what we'll do, we will just find the centroid of this total this figure, right? So how much is this one? This one is 19.5. This one is 91. And this one is 132.3. So 19.5 into 8. 8y, here to here 7, and from here 1. So 1 meter. So 8 plus 91 into 7 by 2, which is 3.5, plus 132.93 into 7 by 3 divided by 243.3. Think but 3.2 meter. Okay. So this PA is actually acting, the point of application is 3.22 meter from the bottom. Okay. So the last problem. Okay. Yeah. So a retaining wall 5 meter high retains a cohesionless soil with an angle of internal friction 35 degrees. The surface is level with the top of the wall and the water table is below the bottom of the wall. Okay. Determine the percentage change on the active thrust if the water table rises on the ground. Okay. So first in dry conditions we will determine, and then we will be determining for the submerged condition. Right. So we will have a 5 meter high wall. So in the first case we'll have the simple this triangular variation, right? So what will be this? This is nothing but 0. See 30, same 35 degrees, so k is same 0.271. 0.271 into 5 into 17. Okay, so what will be PA? Half into 0.271 into 5 into 17. Okay, one just a thing, this gamma is not given. Gamma will be initially 17 kilometer per meter. Okay, this 17, it's given. So what is the PA? So the area of this triangle, right? So this will be 57.58 kilonewton per meter, right? Now the saturated unit weight is given as 20. So what, let us find out the submerged unit weight. It is nothing but 20 minus 9.81, 10.19 kilometer per meter cube. Now the second case we have that this backfill is completely submerged. Okay, water table is at the top, backfill is completely submerged. In that case, will first variation will be like that. For the earth pressure, it is nothing but 0.271 into 5 into 10.19, which is the submerged unit. And the second thing which will be acting is that the lateral thrust due to the water. Okay, what will be that? It will be nothing but 9.81 into 5, right? So now if you want to total it, will be half into 0.271 into 5 into 10.19 into 5 plus half into 9.8125 into 5, right? So if we add this, it will be 157.14 kilonewton per meter, right? So initially, see, in dry condition it was just 57.58 kilonewton per meter, the total active thrust. But as the this backfill soil got submerged, it increased to 154%. If we find out the percentage increase, it will be 154.1 minus 57.58 by 57.5 to 100%, but almost 173%. So almost by 173%, almost by 3 times, I guess, more than 3 times, almost 3 times, it's getting increased. The active thrust is getting increased by almost 3 times, right? So water is actually very dangerous. We should not allow, we cannot allow water to actually uh, remain in the soil. Okay, we cannot have the soil, backfill soil of a retaining wall in submerged condition. It's very, very dangerous. So so when we construct a retaining wall, so proper care should be given for the drainage. So what is done is that here in this part actually we place some, see here we have some a weep hole. Okay, there are weep holes, and also what we can do is that we can place some this geotextile here. Okay, geotextile which can act as a drainage layer. So what will happen is that the water will come here. It will act, so here the geotextile will be acting as both drainage layer and also a filter layer. Why is a filter layer? We'll be discussing all this in the upcoming lectures and upcoming slides. So what will happen is that this geotextile material which we will be placing here, this won't allow the uh, it will allow the water to flow from this soil material to the geotextile, but it won't allow the loss of the soil grains. Okay, it will just allow the water to pass through it. So it will allow the water to pass through it, and what will happen, the water will actually travel through it, percolate through it, and actually get drained out through the weep hole, right? So it will be acting as a drainage material. Yeah, so it's very important that we when we construct a retaining wall, proper drainage, there is consideration, proper drainage has been taken care of. Else the else whenever there is heavy rain and the water the soil gets submerged, there are chances that the retaining wall will collapse if we have not taken into consideration this high active thrust which gets generated when due to the lateral thrust of the water. All right. Okay, so that was all some basic these were some basic problems from the soil mechanics, the basic soil mechanics portion. Okay, so just to revise, just to clear the prerequisites for this course and just to brush up our basic knowledge, we discuss this as because in this first week lecture there aren't any problems to solve, right? So we just revised our concept on the basic soil mechanics. Okay. So now what we will be doing is that we will be actually we will be discussing whatever theory that was taught in this week. So we will be just going from starting all the 3 lectures. We will be discussing little by little all the theories, and we will just like so that it just like freshens up in our mind whatever we have studied in this week. Right. So let us start. Okay, so here are some pictures of some geosynthetic material, right? So I want all of you to identify these for me one by one. Okay, yeah. So I want all of you to please identify all of these for me one by one. So first one, what is that? This first image, this image. If anyone can tell me what is that white colored thing which we can see? What does it seem like? What is that? Yeah, anyone can tell?
Geomembrane?
This one, this first thing.
Yeah, first one is geomembrane.
No, actually this is a geotextile only, normal non-woven geotextile. This is actually used here as a separator. I think it is used here as a separator for some, say, maybe some pavement is being constructed, so just to separate the subgrade and subbase and all these things, this is used as a separator. And also one more thing, this geotextile can also be used as a drainage layer, right? So we will be discussing these things, how this geotextile actually can help as a drainage layer in this. Okay, so what is this thing? The
Geocell.
second one, this one.
Second means
I have ticked.
next one.
Yeah, this thing, this wall thing we can see now, a wall.
So geotextile. Geonextile.
No, this is a geogrid. So you can see these grids,
Geogrid.
right? Yeah, you can see this net like arrangement, these grids,
Geogrid.
right? So this is geogrid, and you can see that this thing which they are constructing here is nothing but a reinforced earth wall. Reinforced, see, here we have some this granular thing, right? Gravels or something. So what they are doing is that this front portion you see is just a fascia, right? So what they are doing is that they are placing one layer of this gravel, then one layer of this geogrid, and then this geogrid is pinched between these two blocks so that the geogrid doesn't move, right? So it's placed between these fascia, these bricks fascia, and then above this again we will be placing some gravels. Okay, like that what will happen is that we can actually make a reinforced geometrical structure, right? So this will, there are many types of, see, all of these have many types. So these geotextiles have many types. You have already said this non-woven, woven. This geogrid has is of many types, uniaxial, biaxial. So we'll be looking into all these things. Okay, then also from the next lecture we will be seeing how to design all this stuff. Okay, so this is a geogrid used. Okay, what is this third one? It's look like a
It,
pool kind of thing, right?
clay liner. Geosynthetic clay liner.
This is actually
Clay
geomembrane.
liner.
Geomembrane.
Yeah.
Yeah, the purpose of
Geomembrane.
GCL, geosynthetic clay liner, and geomembrane are actually
Yeah.
same. So this thing, this below, whatever this thing is actually geosynthetic clay liner. You can see this is the clay which is sandwiched between two geosynthetic layers. Okay, so this is GCL, and this black color thing which we see here, that is actually geomembrane. So can anyone tell me why geomembranes are used? Why are geomembranes used? For what purpose is geomembrane used here? You can see some this pond kind of thing, right? So you can see some. It seems like we will be storing something here, and this thing is lined by this black color material. Polythene is nothing but this PVC and all these things.
It would not allow
Yeah, hello.
fluid out. No? It would not allow fluid out. It
Yeah,
is
yeah.
a contained liquid and
Yeah, correct, correct.
yeah.
So
Yeah.
this is used to contain some harmful liquids, say such as some industrial waste or landfill waste. So for that, so that the harmful material here does not contaminate the good ground beside it, does not leach into the ground below it or beside it, or damage the groundwater below. So that's why what we do is that we use this geomembrane or a geosynthetic clay liner. Both of these are used as a barrier. Okay, this acts as a barrier. This does not allow the harmful gases and the harmful chemicals which are released from the industrial waste or the landfill waste, the household, this MSW waste, municipal solid waste that are dumped in the landfills. So what happens is that it helps to contain the harmful substances within that. It does not allow. So it acts as a barrier. Okay, so here the main this second image, this uh, geogrid is acting as a reinforcement, right? It's reinforcing, and this in the third image, this geomembrane is acting as a barrier. And this geosynthetic clay liner which you see here below, the GCL is also serves the same purpose. It also acts as a barrier, and it does not allow the harmful substances to leach into the soil. So what happens is that if so generally previously what used to happen is that these landfills and all, these were not engineered landfills, just they used to take and dump, right? So what happened, due to that the soil around that place used to get contaminated. Okay, it is, and what the main issue, the main dangerous thing that would happen is that the harmful chemicals that would come out from this waste that would percolate down into the soil, and it would actually damage the groundwater. So if anyone is actually say anyone is actually living nearby and doing a boring for a say this tube well or something well, and he's using that groundwater will be completely contaminated. Okay, it won't be suitable for, it will very this hazardous to human. So to prevent that thing, these barriers are used, so that the harmful chemicals or the harmful gases cannot percolate into the ground and damage the groundwater and the surrounding virgin soil. Okay. Okay, so let us come to this thing. What is this used here?
Geocell,
Yeah,
geocell,
this is a geocell. So geocell uses confinement to actually geocell uses confinement to actually reinforce the soil. Okay, so we place a layer of geocell, and of that we put soil, fill it with soil, and what happens that it gives great strength because of the confining effect of the geocell membrane. What happens is that the soil does not settle, or it strengthens the soil, right? So whenever a geocell is placed, it's not just placed on the ground. So whatever the ground is leveled, after that above that a geotextile layer is placed, above that this geocell is placed, and then above this geocell, and then we actually fill the geocell with soil. Okay, so geocell actually has many more uses, many different uses also. Actually what we can someone can do is that it can also be used for defense purposes, right? So for rapidly say in war lines, whether war is taking place, so what we can do, military people can actually construct a bunker, construct a bunker or a barrier wall which can prevent them, which can save them from blasts and all these blasts and all. They can easily construct a barrier for them using this geocell, right? So this geocell is widely used. All of these geosynthetic materials are still widely used nowadays. Okay, so let us come to this, the figure, the image below the geocell. So what can you guess, what that is? Can you identify that? From this image it might be a little difficult to identify, but still, can you just guess what it might be? You can see some outer covering is there, so inside that some white stuff is there. So can you just guess what it might be? Just a guess. You have studied in the first week lecture you have gone through the lecture, right? So there are, you have studied the various types of geosynthetics. So you have already covered geotextile.
PVD,
Yeah, correct, it's PVD.
PVD.
It's nothing but PVD, prefabricated vertical drains. So here you have a outer covering and inside we have a core, right? So this PVD is actually accelerate the drainage of water in a soil. So what will happen if the drainage of water is accelerated? If the drainage path is reduced and the drainage of water is accelerated, what will happen? It will accelerate the consolidation process, right? Right. So if the drainage
Yes,
path
sir.
is reduced, the consolidation process will be accelerated. So PVDs are regularly used to accelerate the consolidation process, so that something can be constructed over it. So PVDs first these PVDs are installed, and sometimes some preloading is done so that the water so that the soil there consolidates fast. So say if there wouldn't have been any PVD in natural drainage conditions, say it would have taken 20 years, but with the use of PVD, it can be done in say 3 months. Okay, so it accelerates the consolidation process. Accelerates the consolidation process by large amount. Why this is important is that if say there is a soil there and if we construct something over that, and what will happen is that the consolidation will be taking time to happen, right? It will taking years. So what will happen later, when as time passes, there might be some settlement, differential settlements or something. So what will happen, the structure built over it will get damaged. So we don't want that. So to prevent that, what we do is that we want to accelerate the consolidation process, so that let the consolidation process happen. After that after that consolidation process let the maximum consolidation, let it happen. After this consolidation is over, after that only we will construct the structure over it, right? So for that, to actually help the consolidation process, to accelerate the consolidation process, these PVDs are actually used. So this we know this equation, right? This CVT is equal to H drain square into this time factor. So if this drainage, okay, so if this drainage, this actually uh, this drainage path is actually more, the water gets more drainage path, this time will actually reduce. If this drainage path reduces, this time will actually also reduce, right? So what, so our main task by using PVD is that by using PVD we are reducing the drainage path and we are allowing more drainage to occur, so that this time of consolidation also reduces. Okay, and what is this thing here, the last image, the at the center?
Unit.
Yeah, so for what are GNS used for?
Erosion control.
Yeah, erosion control, and one more thing, two main thing, one is erosion control and one other one is
Drainage layer.
drainage. Yeah, so one for drainage and one for drainage. Okay, one is for erosion control and one is for drainage. So you might be thinking that, see, this geo grid and this geonet are almost looking same, but this is not the case. In this geonet, these grids are actually there in two planes. Okay, two distinct planes. So what happens is that this allows actually large flow of water through it. So it's used as a drainage layer.
Three-dimensional control.
Yeah. Okay, so yeah, now yeah, so now let in the next slide I will show. So during my BTech, so we had visited a site which is National Highway 37. So in a portion of National Highway 37, so there was a flyover was actually being constructed. That flyover was actually over a railway track. So railway track was passing through the national highway. So to cross that, so that the traffic passes over that railway track,
Road.
railway track,
Road.
this PVD instead a flyover was being constructed. So the flyover. So in order to, so the flyover. So say this is the flyover. Okay, so say this is the flyover. So this was completely RCC structure, and the approaches were actually decided that these approaches will actually be made with reinforced earth structure. Okay, so these approaches were actually made with reinforced earth structure. So how reinforced earth? These were actually made with nothing but with the use of geogrids. So with the use of geogrids, reinforced earth, the earth was reinforced to make this approaches. So in most of the this you see most of the these flyovers and all you see around in highways and everything, 99% of these flyovers have the approaches that are constructed over this reinforced structure structure. In any, they will be seeing that this in the side there is some like this brick, like this fascia, like this, some management is like that. You might have noticed this is a very common scene whenever you travel in your city, maybe in highways everywhere where there are these flyovers constructed. You will see that on the sides in the approaches, approaches this uh, this blocks like this. So these are nothing but these are just fascias, right? So behind that fascia, behind these fascias, between these fascias is nothing but reinforced soil. Okay, there is nothing but reinforced soil. So the soil is reinforced either with the use of say steel strips. Steel strips are used, or with the help of this geogrid or geosynthetic, whatever, any kind of reinforcing material. Okay, so these are actually used. So what was so in that place, so in that site where I had visited, so in NH 37, so this flyover was being constructed, and here they were planning to make a reinforced make a approach with the help of reinforced earth structure. Okay, reinforced earth structure. And this soil, the below this soil, what they did was this was actually a little soft soil. Okay, the soil, the base, the foundation soil above which the this earth structure, reinforced earth structure of the approach that was to be constructed. This foundation soil is actually was little soft soil. So what was done was PVDs were actually installed to accelerate the consolidation process, so that after the consolidation actually occurs in say 2 to 3 months, then this reinforced earth structure can be built over that. Okay, so this see, so you can see, so these are the machine, this is the machine, drilling machine, using which these PVDs are actually installed. So this you can see, these are actually the PVDs that are installed. Okay, so proper design has to be made, the distance, how the arrangement of the PVD is to be done. So all this, so these PVDs were actually installed. So from all of us actually visited there, and actually saw, we could see how these PVDs were installed by the contractors using this drilling tools. Okay, so after the, now it is actually completely constructed, so traffic is actually moving there now, everything is, construction is complete now. So this picture is from I think 2019. Okay, if I can remember, this is from 2019. So here above, so this is the foundation there. So what was done was these PVDs were actually installed, and this PVDs actually accelerated the consolidation process of this foundation layer. And after this consolidation process was over, above this foundation layer, this approach was actually constructed. This approach with reinforced earth structure was actually constructed. Okay. Okay. So now let us just start revising little by little. So first of all, what is a geosynthetic? Right. What is geosynthetic? Geosynthetic is nothing but what? A natural, it can be natural product, or it can be an artificial product, which is used along with the soil in geotechnical constructions. Okay, geosynthetic can be natural or artificial. Okay, geosynthetic can be natural, it can be artificial, right? So these are natural or artificial products that are used with soil, in geotechnical constructions. So can you give me an example of a natural product which can be used as a geotextile, geosynthetic?
Wire,
Yeah, coir
jute,
or jute.
wire, jute,
Jute is actually very widely used. Jute is very widely used, and there is a jute board. We also have jute board in India. They are also promoting the use of jute for this geosynthetic material. Okay, the square and jute board. This jute is like regularly used. So it is used as a this reinforcing material. Nowadays these duties, geocells are also made with jute. So this jute is actually widely used. It's a geosynthetic material, and this in artificial it can be a polymer, okay, or it can be metal. Okay, polymer, say it can be any kind of synthetic chemical substance, chemical polymer, such as PVC or something, polyvinyl chloride or anything, nylon 66, anything. And this metal such as the steel strips, okay, steel strips are also used for reinforcement purposes. So metals can also be used, polymers can also be. So these are artificials. So this geosynthetics are, as you know, are used in like various cases, right? So from erosion control to reinforcement, right? From erosion control to reinforcement, and I also spoke about drainage purposes. So there are huge number of applications of geosynthetics, right? uh, uh, Mainly you can there are things called geobags, something which are also geobags. Geobags are bags which are filled with soil, and those are actually uh, kept in the river banks, so that there is less erosion. Okay, there are many things like these geogrids are also used to reinforce the slopes. Then this geo this one geocells are also used to reinforce slopes. So there are huge many uses of geosynthetic materials. We already discussed some of these uses, such as we discussed the use of this geomembrane, which is used as canal lining. These are used as lining in canals where water used to be transported across large distances. It is used as a lining for as a barrier material for in landfills. So there are many uses of each geosynthetic material, right? Now, traditionally, see, if you go into history, from historical time, from prehistoric time, also this people knew that if we reinforce the soil with some material, say twigs or some bamboo or something, the strength of the structure actually gets increased, right? And this actually was known to man since many years, but this concept was actually like brought into the technical field as reinforced soil structures by Henry Vidal. So Henry Vidal actually reinvented this thing, the concept of reinforced earth, right? So now one more thing is that there is a misnomer, that geosynthetic or geotextile. So previously, there was a confusion between the term geosynthetic and geotextile. So geotextile was actually used invariantly with all kind of geosynthetic material previously. But now, see, now this thing has been made completely clear by the International Geosynthetic Society. This geotextile is a kind of geosynthetic, right? Previously, all geosynthetics were called geotextile, but that is not the case. We know that now, right? So there are many types of geosynthetic material. One of them is geotextile. So the main governing body, or the main international organization which actually looks into this is the International Geosynthetic Society, right? So they,
Recording in progress.
yeah, sorry, okay, there is some issue with the internet connection, that's why. Yeah, yeah, okay, so I hope it's visible now. Right. Okay, so Yeah. So the International Geosynthetic Society is actually the society which is a governing body which actually deals with all the research related to geosynthetic material, right? Now, first let us revise some of the uses of this geosynthetics that were actually discussed in the lecture. So the first thing that was discussed was as a separator, right? So geotextiles. So say we have a subgrade here, okay, and we have a aggregate layer, okay. So that the subgrade and there is no intermixing of the subgrade and the aggregate. So what is done is that we place a geotextile layer, and this geotextile layer actually acts as a separator, right? So there is first this use was that is of separator, right? Next is filtration, right? So filtration, how filtration? So this geotextile will actually allow water to actually pass through this, okay. It will allow water and then it will allow the water to drain out through it, but it won't allow the soil particles to pass, right? So that's why filtration. And then the most important property, reinforcement, right? So we saw that the structures such as say reinforced earth structures, say the say uh, reinforced earth structures are actually can be constructed with the help of geosynthetic material, any kind of, it may be geogrid, it may be geotextile. So there are layers of geotextile or geogrid that are placed, and these layers are actually, so first what we do is that say there is one layer of soil, then one layer of geosynthetic material, then one layer of soil, one layer of geosynthetic material, like this earth structure, reinforced earth structures are actually constructed, and this geosynthetic material is actually tied into the fascia walls. The walls that we see here, these are just for acting as a fascia. These don't have actually any, these don't have any other property. These just have to give a good look. So this fascias and also fascia is used so that the wall actually looks good, right? So this fascia is used to hold the geosynthetic in position, to tie the geosynthetic here, and also to give a good look, okay. Then geosynthetics are also used for this erosion control, as we discussed. Erosion control, these geonets and all are used as erosion control devices. Geonets, geotextiles are also used for erosion control, okay. Then drainage, we already discussed the case of drainage layer. We discussed in the case of retaining walls, right? Here geotextile can be placed so that water actually drains out. And also in case of pavement, so in case of pavements, what we can do is that here we have drains, right, at the edge of sides of the pavement, and here we have the pavement. So any water, say this is a geotextile layer, okay, so any water here can travel into the geotextile, through the geotextile, and then get drained out, okay. So geotextile also acts as a drainage material. Now what are the main types of geosynthetics? First is geotextile, most common, geotextile. Then we have geogrids, then we have geonets, then we have geomembranes. We saw the images of all these things, right, in the first slide. Geomembranes, then we have PBD, we have geosynthetic clay liners, right? We have geocells, geocells, and also we have geocomposites. Geocomposites are nothing but geosynthetic material formed with the help of, say, uh, more than one kind of geosynthetic material. For example, say you have a geonet, okay, say you have a geonet here, and above the geonet you can, what you can do, above and below you can sandwich the geonet between two geotextile. So this geotextile will be acting as a filter material, right? It will just allow water to pass through it and not the soil. It will just allow water to pass through it, and this geonet will actually act as a drainage layer. So this whole arrangement actually forms a geocomposite, right? So geonet along with the geotextile we can form a geocomposite. So geocomposite is nothing but geosynthetic material that are formed with more than one type of geosynthetic material. Okay, so now there are many types of geotextiles, right? We already studied woven, there are non-woven, right? So there are woven, there are non-woven. Okay, there are, so woven, this there are, so these are actually differentiated on the basis of the procedure of the manufacturing procedure. So the manufacturing procedure of woven geotextile is different, and that of non-woven geotextile is different. So woven geotextile will be something like a knitting structure. So this textile that we are wearing, this is also textile, right? This is this cloth. This clothing is actually woven. If you see closely, you can see that it's nice. There are some definite patterns in it, right? So it's woven in a with a machine, right? It's properly woven. It's properly knitted. So that forms a, similarly we construct a geotextile. So geotextiles are also nothing but this is also a textile. Geotextile is also a textile, right? But the purpose of those two, the strength of these two are different, right? So the, so geotextile are two types, woven and non-woven. So woven, you will see that there is a good pattern, knitted pattern uh, in the geotextile. So just by looking and touching the geotextile, you can differentiate whether it is a woven geotextile, whether it is a non-woven geotextile. So all these images, everything was actually shown to you during the lectures. So I hope you can recall all those things, right? So now we'll just go through whatever was taught, right? So also uh, both natural and artificial, there are two types of geotextiles that we discussed. Both of them can have these two types, woven also, non-woven also. Okay. Then we have these geogrids. Okay, so geogrids are basically uniaxial or biaxial. Uniaxial means the main load, it can take load in only one direction, and biaxial mean it has strength in both the direction. That means it can take load in both the direction, both in this direction, say in both in this direction, both in this direction. And uniaxial can only take in one direction, right? So where are uniaxial geogrids mostly used? So uniaxial geogrids are generally used as reinforcement layers in embankments or RE walls, reinforced earth walls. Okay, in RE walls or embankments, where say where generally where the this out of plane direction is very long, right? So embankments are long structures, right? Very long structure, very big structures. So in that cases, uniaxial geogrids are generally used, and biaxial geogrids are generally used below road to reinforce the road. Okay, so that is, say you have a small portion of a pavement, you want to reinforce the base of that base, the subgrade of that pavement. So in that cases, we use the biaxial geogrid, and also maybe below railway tracks. Okay, railway tracks, and in all those cases, we will use the biaxial. And the geogrids also have different manufacturing process. So one is this extra, I think, if I can remember, one is your knitted and one is the this one stretched. So stretched, this stretched kind of geogrid, what is done is that, say if some material, okay, so some holes are punched and some with the help of some machine, these things are stretched. So what happens with that stretching, these geogrids form. Okay, and knitted means nothing but there is kind of woven thing, right? So it's weaved, woven. So geogrids are actually woven in case of knitted, in the case of knitted. Right. Okay. So we got geotextile, then geogrid, and next comes our geonets. So geonets we already discussed. These are actually used for what? Drainage purposes, right? Drainage purposes, because the nets that form the geonets, they are in two different planes. As they are in two different planes, they allow the water to pass through them easily. So they are used as drainage layers. Generally, geonets are also used for erosion control. They also prevent erosion of slopes. So in both these cases, they are used. And one more thing, geonet. The other name of geonet is also geospacer. Okay, someone can ask you, what is the other name of geonet? So always remember that geonets are also called geospacers. Okay, so geonets are also commonly used sandwiched between geotextile layers that we already discussed one slide back. Okay, so mainly is used for erosion control and your drainage purposes. Okay, Ero erosion and drainage. Now next comes geomembrane. Okay, so geomembrane we all already discussed. These are used as barrier, right? Geomembranes are used as barrier or lining. So it may be landfill lining, it may be canal, it may be tunnel. Okay, these are used as lining material. So in landfill, these are used as barrier material to prevent harmful gases and harmful chemicals from leaching into the ground and into the atmosphere. These landfills, these geomembranes are actually used. Okay, second is canals. In case of canals, these geomembranes are actually used as a lining. So what happens? So you have canals like this, right? So canals are actually used to carry water, to transport water across large distance. So what we can do is you can put geomembrane. So with the use of geomembrane, we don't have to make the canal lining with concrete, first thing. And the second thing is that the construction process can be accelerated. So directly above the soil, what we can do, yes, directly above the excavated soil, we can put the geomembrane. So this will actually prevent the water from damaging the soil layer and also the water from leaching into the ground or going to the ground. So just as a say you have a ground and you are putting a polythene or polythene or something plastic thing over it. So it will prevent the water from it will trap the water inside it, right? So the same thing. That's all. Ah. Then comes PVDs, right? So as we discussed, PVDs are used to accelerate the consolidation process. So what is done is, say this is a soil layer, right? So this is a layer of soil. Generally, say below this is it can be one way drainage, two way anything. Say this is impervious. Okay, this is impervious. Say this is impervious. So in if there are no PVDs, the water has actually one drainage path. Which is a drainage path? The drainage path is this, to come out of this, right? The water only has one path to come out. But in that case, what happens? The process of consolidation takes several years to complete, right? The consolidation process is very slow. So what we can do is that we can put PVDs in the soil. Okay, so we can put PVDs in the soil. So what will happen? So water from here will come here, can go here. Water point from this point can travel here. So after, so what happens? The drainage, you are increasing the drainage path, not the length of the path. By increasing the drainage path, I mean we are giving more scope to the water to drain out. So what happens? The water comes here, it drains out. So the path is reduced by the length of the drainage path is reduced, that is first, and we are giving more scope for the water to drain out. So what happens is that the water will, so some preloading is done, so some loading is given, so some preloading is given with some surcharge, okay, some soil fill. So what happens, due to that the consolidation process is accelerated by a large amount. Okay, so these are highly permeable. So inside that, so this is, so there is one, so there is one outer cover, and inside that there is some core. So outer cover actually allows only the water to pass through it. It acts as a filter, it does not allow the soil to pass through it. So the water will come here, it will come to the core, and it will drain out along the core, seep out along the core. Okay, so it reduces the length of the flow path, and thereby it accelerates the process of consolidation. Okay, so these are also used extensively. Okay, and I also showed to you how these are actually installed in the field. Also the machine, I showed you the machine, drilling machine. Okay, okay, so next is our GCL. So what is GCL? GCL is nothing but geosynthetic clay liner, right? So geosynthetic clay liner is actually mainly composed of a bentonite clay core. So bentonite is highly impermeable clay substance, right? So a bentonite core is there, which is sandwiched between some geotextile layer. Okay, so mostly non-woven geotextile. So we have a bentonite here, and here above that and below that we have non-woven geotextile. Okay, so the main purpose of this GCL is that, same as geomembrane, it also acts as a barrier. Okay, it does not allow, as this clay is highly impervious, as it is highly impervious, it does not allow anything to pass through it. Okay, okay, and this bentonite is actually having a self-repair property. Self-repair property. Why self-repair property? What happens, what is when, if you remember from, you have studied the properties of bentonite, I hope so, in the basic soil mechanics in the first chapter only. This we are taught about the clay mineralogy chapter, right? Clay minerals and all these things we are taught in basic soil mechanics. So in that chapter also we have learned about this bentonite thing. So the main property of bentonite is that it's highly expensive, right? As soon as it comes in contact with water, it's highly expensive because it has large this plasticity index. Okay, huge plasticity index. So it's very expensive. As soon as it comes in contact with water, it will expand, right? So due to this expansion, what happens, if there are cracks in the clay layer, as soon as it comes in contact with little bit of water, the bentonite expands, and the cracks in that bentonite layer actually get filled due to this expansion. So it has a self repair property. So all the cracks get closed, repaired up as soon as it comes in contact with water. What happens, the water gets stopped, it cannot pass through it, right? So this is a natural substance. Bentonite is a natural substance which you can use to used as a geosynthetic material. Okay, next we have geocell. Geocell. Okay, so geocells, as we already discussed, we saw the image also of geocells, right? So geocells are, these are hexagonal, mostly hexagonal, this box kind of thing, right? So due to the confinement of, whenever we fill the geocells with soil, right? So whenever there is load on that soil, inside the geocell there is a confinement, there is uh, confining effect. So due to that, what happens, the soil actually gets strengthened, so it does not allow the soil to settle or anything, right? It strengthens the soil. So the main property this of geocell is that it's a confinement product. It's reinforces the soil with the help of confinement. Okay. So just simple, in a simple way, if you want to understand this confinement property, say you have a soil specimen. You are doing the triaxial test. Okay. Say you have sigma 3 is equal to 0. Means this cell pressure is actually 0. There is no confining pressure. In that case, if you keep on increasing the deviating stress or the axial load, say it will fail at say it will fail at sigma d1. Okay, it will fail at this deviating stress. Now say if we increase the confining stress to say 20 kPa, at that time this will fail at sigma d2. So which is greater? Sigma d1 will be greater or sigma d2 will be greater? From common sense. In the first case, there is no confinement. You are doing a triaxial test, but it will be not a triaxial test. It's just a UCS test, right? So the confining pressure is 0. Say it fails at this sigma d1 deviating stress. Then what do you do? We put some confining pressure on the soil sample, and then we do the test. And then obviously this sigma d2, the failure deviating stress for the second case, it will always be more, right? Why? Because of confinement effect, isn't it? So that's the so this is the same property with which this geocell actually works. This is a confinement product. It confines the soil. So this confining pressure which is acting on the soil is actually strengthening the soil. That's all. So where are these geocells used? These are also used as erosion control devices. These are used to protect steep slopes. These are used to build retaining walls. Okay, reinforced earth walls. Also as the sub-base support such as road bases, then these railway tracks. All these things, these are used. Okay, just a second. I will just show you one image. Okay, just let me open Google Images. Just a second. Yeah. So see, just see this image. Huh? Yeah. So this was actually this is a portion of NH44. This portion actually was the main highway. That is the main highway connecting between this Assam and Tripura. This is the main highway that connects the state of Tripura to the mainland India through Assam. Okay, there is a place called Churaibari. Churaibari is a place between the border of Assam and Tripura. Okay, so this was the condition of the road. So every time when they are in after this monsoon season, this monsoon is going on, right? So every time after this monsoon season, what is to happen? The road condition is to be something like this. That is shown here. Okay, so after that, what happened? What was done was this geocell was used. So the engineers decided to see the section schematic of the section is shown here in the figure 2. We can see that there is a subgrid, then we have the geotextile was placed as a separator, and then above that there were two layers of geocells that were placed. This Tata Web geocell it's written, right? So 2 layers of geocells were placed to strengthen the base of the soil, and above that, then regular your bituminous this concrete this road was constructed. Bituminous road above the granular base was constructed. So initially we have a subgrade here. Above that, a geotextile was used as a separator. Above that, these 2 layers of geocells were used. Above the geocell, this granular base, and normal this road was constructed. Okay, so this was the initial figure one. This figure one was the initial condition of the road. Okay, and this road after after this construction, after 2017, even after heavy rains, you can see the road is intact, nothing. Initially, just after heavy rain, this the condition used to be horrible. You can see here, these trailers, heavy trailers are unable to go. Just see the condition of the road after rain. This used to be the condition of the road after the rain. But after the use of geocell, even after the rains, you can see the road is perfectly intact. Such like it seems that it just has been constructed new. Okay, so this is the power of this geosynthetic material. Okay, these are the power of geosynthetic material. Okay, so geosynthesis actually changed the how geotechnical engineering is done by a large extent, right? You can see this is the main highway that used to be affected, affected every year. So just using geocells, a simple solution, this problem could be solved, right? Okay. Okay, so and one more important thing is that say geocells are actually used for the slope thing, this to build slopes, to protect slopes. So what happens in the geocells after some months or some years, automatically vegetation actually grows up. So it actually looks very beautiful also in the slopes. All right, and yeah, the last is geocomposite. Geocomposite we have already discussed. So more using more than one type of geosynthetic material together will form a geocomposite. Okay, such as a geonet with geotextile, a geogrid with geotextile, and so on. Right. So these are nothing but geotextile. And there are other geosynthetic material also. Those are say geopipes. So geopipes, these geopipes are actually used along the to put erosion control, river erosion control structures. Okay, these geopipes are actually used so that the erosion of river can be prevented. If I remember, I can show you one picture. Okay, just let me show you the picture of geobags. I think you have seen geobags. Yeah, yeah. So you can see this image here. So see, these are bags, nothing like sacks. Okay, sack. These sacks are filled with soil, and they are placed in this arrangement along the river banks. So what happens is that due to this geobags, they prevent the erosion of the river banks. So if you know uh, this it's written Majuli here, right? So Majuli is actually the largest riverine island. Okay, that is in the Brahmaputra river, right? Majuli is the largest river island in this world, I guess. It is the largest river island in the world. So Majuli is facing a long problem since like many years. The main problem is of erosion. So Brahmaputra is actually eroding eroding the soil of this land. It's taking the soil of this land with it. So what is happening? The area of the land is like constantly reducing. So uh, many ideas are suggested regularly by many engineers. So here you can see one of the ideas, that is geobags. So geobags are nothing but bags like sacks, okay, rice sack or something. Similarly, same to that, these are made with some geotextile material. Okay, so inside that soil is there, and it actually prevents the soil from erosion. Okay, here also you can see bank erosion protection, same in Brahmaputra, same geobags were used. Geobags are used. So these are geobags over these round things. Those are geobags. Those are placed over a geotextile layer. Okay, so the base layer, this base layer is nothing but a geotextile layer which prevents the which acts as a filter material. So it does not allows the soil to pass, but it allows the water to pass through it. Okay, the base geotextile layer is actually acting as a filter layer. So it's acting as a filter layer because it doesn't allow the soil to pass through it, but it allows the water to pass through it. So you have a geotextile layer in the bottom, and above that these geobags are placed. So this arrangement actually prevents the erosion of the banks, river banks. Okay, similar to that, there are many things. Uh, yeah, so one more thing is this one, your stone column, geosynthetic NK stone column. So stone columns are also structures that are built into the soil so that the strength of the soil gets increased. Okay, the soil gets some rigidity. Okay, the strength of the overall soil gets increased. Okay, and also it allows little bit drainage. So that stone columns, if it encased the stone columns, so these are some columns, right? Like this, stones with the stone. Some columns are made inside the soil. There are some specific drilling devices with which these are made. So if these stone columns are actually encased by say geogrid material, what happens? It is seen that the strength of the stone column or the rigidity of the stone columns actually increase. So if any structures, there will be many stone columns like this. So if any structure is actually built over that, the settlement will be far more lesser if encased stone columns are used. Okay, these stone columns, these are actually encased with geogrid material. So this is also one of the uses of this uh, geogrid material. And also one more thing that is widely used for erosion control is gabion. Gabion are nothing but big net like structures. Okay, the gabions are filled with rocks or whatever is available nearby. Rocks, generally rocks only, rocks or boulders, and those are actually placed in the river banks or maybe in the below the slopes. Okay, below the slopes for toe protection, for the toe protection of the soil slopes here like that. So those are some net-like structures, and those are actually filled with uh, these boulders or rocks, and those actually prevent your erosion. Okay, so these are all about the geosynthetic material, and then comes the this uh, one of the most boring part, I will say, when you will study. When I studied this course during my bachelor's, that time also this topic was actually quite boring. The next topic is this polymers. Okay, this is nothing but chemistry. Okay, I hope you can just, but it is actually very important for us to study. Why is it important? Because say you are an engineer, okay, so you have a huge project, a very big project where you need to use this geotextile material. Okay, so huge, crores and crores of project, and you want to place order for crores of this geotextile material that you want to use in your project. Now there are many vendors in the market. Now how will you ensure that what product that vendor is sending you as a sample, or what product the vendor has sent you is actually correct, or it's actually what is actually been specified? Okay, that product is actually what you want. How will you actually do that? So to understand that, what we do is that there are many tests. which we say which we can do to determine the polymers or the material that forms those products. Okay, so there are many tests, material science tests that are done to identify the constituent polymers that build up that geosynthetic material. So for that reason, actually, it's very important for us to study this chapter. I understand that it becomes a little bit boring, this topic, but it's, so in that sense, it's very important for us to study, because as an engineer, we need to ensure that whatever product we are using in our project is correct, right? And how will you ensure that the vendor that the product is providing is what was actually mentioned in the document? So actually what we do is we generally test a little sample we will take, we will do with some there are two types of tests, right? So one test will be the physical characteristic, the strength characteristics, the test, say the this the this the tensile strength of the geosynthetic material, the punching resistance of the geosynthetic. All these tests we will actually see. The strength test we will study in this course. We will also study. So these tests are one type. So second type of test is the material. What material is actually being used? So for that reason, this polymers is actually you should know that what polymers are actually forming the geosynthetic material that you are using, so that when you test the geosynthetic material, you can say that that geosynthetic material is correct or not. It has the proper proportions of that polymer or not. So in that sense, is actually important. Okay. So polymer, what is polymer? Polymers are nothing but combination of monomers actually make a polymer, right? A monomer are the basic single units that combine to form a polymer. Okay, so there are mainly this two types of cross-linking polymer, that are thermoplastic and thermoset polymers. So thermoplastic are those that can be repeatedly heated and molded and then reheated and molded, okay, in different shapes. Those are your thermoplastic polymers. And the other is the thermoset polymers, is that once you heat it and mold it again, if you heat it, it's gonna get degraded. Okay, you cannot use that. So these are the main two types of cross-linking polymers. Okay. So now I won't go into the details, but it's very important for you to study. Okay, please study all the composition and properties of all these polymer and their formulation, such as polyethylene, this polypropylene, polyvinyl chloride, then this polyamide polystyrene. All these things are important, and also it's important for you to know this. You should remember that which geosynthetic material uses which kind of polymer. Okay, so polyethylene, geotextiles, geomembranes, geogrids, geopipes, geonets, geocomposites. Okay, all these things are made up of polyethylene. Then next is polypropylene. Polypropylene only geotextile, geomembrane, geogrid, and geocomposites. Then polyvinyl chlorides, PVC. By closing your eyes, if anyone doesn't know only anything, okay, you can see that you can say that this geomembranes, okay, right? These geomembranes are made up of PVC. This is just obvious, very obvious. Geomembranes, then geocomposites, geopipes, right? Then we have after that polyester. Polyester is also used to make clothing, right? Also used to make textiles, right? Synthetic textile, polyester. So these are used to make geotextiles, geogrids. In that way you can remember little things. Okay. Then we have polyamide, PA, that is nylon 66, that is used for geotextiles, geocomposites, geogrids. Then we have polystyrene. Polystyrene is geocomposites and geofoam. So geofoam, what is geofoam? Geofoam is nothing but you have seen thermocol, right? We did not discuss geofoam earlier, so I am discussing it now. You have seen thermocol earlier, right? So thermocol, geofoam is something similar to thermocol. Right? Very lightweight foam kind of material, had high compressive strength, and it is very lightweight. So these are used for to construct embankments as backfill material in retaining walls very often. Okay. Now then the thing that I was uh, discussing was the identification. Say you get a sample and you want to test that sample. So there are different methods of testing the sample, such as burning characteristics, thermogravimetric analysis, TGA, DSC, then induction time YT, thermomechanical analysis, dynamic mechanical analysis, chromatography, molecular weight basis. So all these different identification methods are there, with which you can use to determine the constituent polymers or um, uh, constituent polymers that form your geosynthetic material. Okay, so please study all this, go through this all these types. Okay, then we have the manufacturing of this geotextile geosynthetic material, right? So as we discussed, these are nothing but textile, type of textile only. Say geotextile is also a type of textile. So these are made up of fibers, right? So fibers are made from polymers. So first is monomer, combination of monomers form. First is monomers from polymers from these fibers, and your these fibers actually form yarns. Okay, then yarns actually form then textiles. Okay, so there are different types of polymers actually form our fibers, and these fibers then form different types of yarns, and with the help of these yarns, these textiles are actually constructed. So please go through the different types of yarns. I won't repeat it again and again. So please go through all the different types of yarns. Okay, so now how different types of geotextiles are manufactured. So woven, there are, there are types of geotextiles: woven geotextile, non-woven geotextile, we already discussed. Okay, so there are different types of weaving based on which you can differentiate it. Then in non-woven geotextile you can differentiate how they are bonded. Maybe they are needle punched. So all these images you can get in the internet easily, and also in the slides the Professor Gopal had already shown all of this to you, right? So non-woven fibers, those are bonded fibers, or they're bonded with the help of resins, or they are punched with the help of needles. So there are many techniques with the help of which woven and non-woven these geotextiles are formed, right? Then we have geogrids. So geogrids are mainly formed by extrusion or weaving or welding processes. So extrusion, so all this, how is the process of geogrids are actually, how, what is the process of manufacture of geogrids? Please go through that in detail. All the manufacturing process you should know. It is very necessary for us to actually at least know, have the basic idea how they are actually manufactured. Okay, if someone why is it important is because, say some vendor comes to you and tells says to you that our geotextile or geogrid is made with the help of extrusion method. Then you should know that what is actually extrusion method. That should the picture of extrusion method should come to your mind. So in that reason, these things are actually important for us to study. Okay, I won't go through the details, so please go study yourself all these things, right? So that will be all for this class. So I suggest that we already solved. So in this today's lecture we solved some basic problems from basic soil mechanics, and then discussed the different types of geotextiles and polymers and the uses of geotextiles, and this the formation, how the geotextiles are actually formed. All these things actually we study, right? And please study, or please always keep in mind that which geosynthetic can be used for what purpose. So there are many purposes we discussed, right? Filtration, reinforcement, separator, drainage, all these. There are many barrier. These are all, see, filtration, then separator, then barrier, then drainage, then reinforcement. Okay, like this, there are uh, many functions of geosynthetic material are there, right? So which geosynthetic material is used for which function, That should be clear in your mind, right? So I suggest that you please go through the lecture and please revise. Always keep on revising and always keep that in mind, that which geosynthetic material is used for which function, which geosynthetic material is for filtration, which geosynthetic materials can be used for drainage, like this. Okay, so if someone asked you which someone asks you, can geomembrane be used for filtration, what will be your answer? Can geomembrane be used for filtration? Please tell me, can geomembrane be used for filtration purpose or drainage purpose? Can geomembranes be used? No, right? Geomembranes cannot be used for drainage purposes or filtration purposes. For that, you have to use this geonets or geotextile. What is the use of geomembrane? Geomembrane is only used as a barrier. Okay, nothing else. It has just one purpose, that is barrier. So you always remember all these functions: B, D, E, F, P, R, S. Right? Barrier, drainage, erosion control, filtration, protection, reinforcement, separation. Okay, you remember all these things and try to correlate which geosynthetic material can be used with which this which function. Okay, which geosynthetic material can be used for which function. All geosynthetic materials cannot be used for all. Geotextile cannot be used as a barrier material, right? You need to use geomembrane for that. So everything should be clear in your mind, that which geosynthetic material can be used with which function, used for which function. So as we progress through the course, automatically this will get cleared up one by one, but still these things should be clear, okay, from the beginning. Then it will be easier for you. Okay, so that's all for today. Thank you so much for attending to this interactive session, and I wish that it can be more interactive, because today only one of you was answering and one of you was interacting. So I wish that from the next class, all of you please contribute to this, because this is not a class, right? It's just a normal interactive session. Okay, I am not some professor or something. Okay, I am also a student, a PhD. I am also doing a PhD. I am also a student. I am also learning. So it should be a two-way process, right? So I hope that this will be more of an interactive session than a one-way just at everybody course. Okay, this one-way session you can already watch the videos, right? So what is the use of this session? It should be interactive. Okay, you can ask questions. I can also ask some questions to you. We can discuss and solve problems, right? Okay, so that's all for today's class. In the next session, next interactive session, we will see whatever has been done. We will discuss all these things, and if there are any problems, we will solve those problems. Okay, so if there is any doubt, you can always contact me on my email or anywhere, right? And as I told you, please go through that polymer chapter, because it might be a little boring for you, but the manufacturing process and the polymer, what kind of polymers, that is also very important for you. So please keep that in mind and read that chapter nicely. Uh, and also I request you to I will request you again to keep like to make clear in your mind. The clarity should be there in your mind, that which geosynthetic material is used for which function. Okay, that should be clear in your mind. Okay, so I request you to please go through this whole thing, and also the week 2 lectures are already released, right? So you will go through that. So I hope that all of you will do well. Okay, so thank you. So with that, we will end today's session. Okay, thank you for attending. So this video will also be uploaded, and the link will be shared with you from NPTEL site. Okay, so thank you for attending. uh, have a good evening.